So I'm here on the Wikipedia page for a certain scientific law called the inverse square law. And so let's read this. A specified physical quantity is inversely proportional to the square of the distance from the source of that physical quantity. So here we see an example of inverse proportion essentially in the wild here on Wikipedia. So scrolling down a bit, it says, for example, that if you're dealing with the strength of gravity, the force of gravity gets weaker as you move further and further away from the source of that gravitation. For example, as you move further and further away from the center of planet Earth, the force of gravity on your body becomes weaker. It says this works for light, for example. As you move further and further away from the source of a light, the apparent brightness, the apparent intensity of the light that you perceive goes down, and it goes down according to inverse square law. And it works for other things. It works for sound, and it works for some electrostatics. And today I would like to do a particular example problem of inverse square law in the case of light. And so I've translated the law here into this particular situation. The intensity of a light is inversely proportional to the squared distance from the source of the light. And so the question is, if the intensity of a light is 80 lux at a distance of 3 feet, what happens to the intensity if you move 1 foot further back and you're now observing the light from a distance of 4 feet? So to begin this problem, I would like to start by setting up an equation that captures this statement right here. Intensity is inversely proportional to squared distance. Now I think the real wrinkle here, and the one that's easy to overlook, is this term squared here. If I wanted to translate this statement into an equation, I might start by using I for intensity. I for intensity is equals sign inversely proportional, so K divided by. Inversely proportional to what? Inversely proportional to distance? No. Inversely proportional to the squared distance from the source. So to capture this law, I would have to write down I equals K divided by distance squared. Now that, I think, is the hardest part. Translating the statement that you were given in plain English into an equation. But now let's go ahead and use that to answer this question. If the intensity is 80 lux at a distance of 3 feet, what's the intensity at a distance of 4 feet? So let's go into our equation, and step 1 is always to find K. Find the constant. So I will do that by plugging in the intensity of 80 in I's position, and I will plug in the distance of 3, but I can't forget that the distance is squared distance from the source. So if I go ahead and solve that for K, 3 squared is 9, so multiplying both sides by 9, I get a K value of, I think, 720. So then they say, well, what if you change the distance to 4 feet? Say, okay, the distance is 4 feet, then what's the new intensity? I'll use the K value that we just obtained and the new distance of 4, the new distance of 4. But I can't forget that 4 is being squared. So the new intensity would be whatever 720 divided by 16 is. I'll leave the decimal approximation to you as an exercise. So this is how I would solve a problem of this nature using a law that has a power in it, square.